We have already proved that the derivative of sine x is cosine x and the derivative of cosine x is negative sine x. We're going to talk about using the quotient rule to find the derivatives of other trig functions. Our book does this derivative, that the derivative of tangent x is secant x squared. We are now going to do the proof that the derivative with respect to x of secant x is equal to secant x tangent x. So derivative with respect to x of secant of x, that's equal to the derivative with respect to x of secant x is the same as 1 over cosine of x. So using the quotient rule, that's low cosine of x d high, derivative of 1 is just 0, minus high, that's 1, d low, derivative of cosine x is negative sine x, all over the bottom squared, all over cosine x squared. And so now we can simplify that. That's 0 minus a negative, so plus sine of x, all over cosine x times sine times cosine x. Cosine x squared is just cosine x times itself. And so we could rewrite that as sine x over cosine x times 1 over cosine x, just rewriting that fraction. And so that's the same thing as sine x over cosine x is tangent of x, and 1 over cosine x, as we saw above, is secant of x. So we can find the remainder of these derivatives just using what these things are equivalent to. Each of these other than sine and cosine, each of these is equivalent to some fraction of sine and cosine. So tangent of x, remember, is sine x over cosine x. Secant of x is 1 over cosine of x. Cotangent of x is the opposite of tangent of x, or the flip of tangent of x is cosine x over sine x. And cosecant of x is 1 over sine of x. So that's how those four trig functions are related to the first two. So for each of these, we can use just the quotient rule, and in this case and this case, we also use one trig identity to get that nice secant squared x and negative cosecant squared x. A few things that are worth observing when you look at these derivatives of trig functions as a way to help you remember. One thing to remember is that all the trig functions with a co in front of them, have a negative in front, and all the trig functions that are not co are not negative, have a positive in front. So that's one thing to help you remember some derivatives of trig functions. So as a quick example, we could find the derivative with respect to x of, let's say, x cubed times cotangent of x. We need the product rule for that. The first times the derivative of the second, that's negative cosecant squared x, plus the second cotangent x times the derivative of the first, 3x squared. And so that's negative x cubed cosecant squared x plus 3x squared cotangent of x. Let's also use the quotient rule to prove the power rule for negative integers. So we know that the power rule in general is true, that the derivative with respect to x of x to the n is n times x to the n minus 1 for any real number n. So n could be pi, n could be negative 406.2, n could be 12, etc. But so far we have only proved for n a positive integer. And I said that we'd prove it for other values of n as we proceed through the course. Let's now do the proof for n a negative negative integer. So let's suppose that n is a negative integer. That means that n is less than 0. And we're taking the derivative with respect to x of x to the n. So we know that that's the same thing as the derivative with respect to x of 1 over x to the negative n. So a negative exponent just flips the fraction down. So we've sort of done that twice. So x to the n is the same as 1 over x to the negative n. And since n is less than 0, that means that negative n is greater than 0. And we were talking about an integer, so this is an integer that is greater than 0. And we've already proved, we know what the derivative is for x to a positive integer. So we can use the quotient rule on this. This is low, x to the negative n. D high, derivative of 1 is 0, minus high, 1. D low, derivative of x to the negative n. Well, negative n is a positive integer, so we know its derivative. That is just bringing the exponent down, negative n times x to the negative n minus 1, subtracting 1 from the exponent. And now we're continuing to use the quotient rule, all divided by the bottom squared, x to the negative n squared. So that's x to the negative n to the second power. All right, let's simplify that. So this is just 0, so we don't have to worry about it. Negative times negative, so that's positive, n x to the negative n minus 1 over x to the negative n to the second power. When we take the exponent of the power, we just multiply the exponents. That's x to the negative 2n. So continuing to simplify, remember that x to the a over x to the b is equal to x to the a minus b. So we can subtract those exponents. This is n times x to the negative n minus 1 divided by x to the negative 2n, so minus a negative 2n. And that's equal to n times x to the negative n minus 1 plus 2n. That's n times x to the 2n minus n, that's just 1n left over, minus 1. And so what have we shown? We have shown that the derivative with respect to x of x to the n is exactly what we know it is by the power rule for negative integers n. So as I said before, we'll continue to expand our proof of the power rule to extend to all real numbers eventually, but now we know that it is true for positive integers n, and we know that it's true for negative integers n. We are going to continue using it, but the proofs that it works for everything, all values of n, will follow throughout the course.